Hello everyone, I am Monika Bhushan and today we are starting lecture number 15 of partial differential equation. In today's class we are going to see solution of one-dimensional wave equation. Okay, in last class we had seen derivation of one-dimensional wave equation, right? So we had seen in detail the concept of wave equation and we had taken few examples also, right? So if you had not seen derivation, so I will suggest you first you watch this derivation, then only come to solution of one-dimensional wave equation. Otherwise, few concepts you will not understand. Okay. So for solution of one-dimensional wave equation, actually we have many methods, fine. So we have different methods to solve one-dimensional wave equation. But the method which we are going to see today is called the separation of variable method. So before starting the solution, we will little bit discuss this method, that what is called separation of variables method and why we are taking help of separation of variable method to solve one-dimensional wave equation. Okay, so separation of variables method is actually useful to solve differential equations and few types of partial differential equations also. So we will just take one a simple example of differential equation before jumping to partial differential equation that is needed for today's session. So if I'll take one simple example of differential equation, suppose I am taking one example, dy by dx equals 5xy. Okay, we can solve this differential equation using different methods also, but we are going to use separation of variable method. So basically we need to understand that where we are allowed to use separation of variables method and in which differential equations or in which partial differential equation we will not be able to use separation of variables method. Okay, so here what we see that we have two variables present, correct? No, one is x and one is y. So in any equation, if we have two variables present, okay, and if we can rearrange this differential equation so that one type of variable will be present in one side, suppose left hand side, and second variable can be taken to the right hand side. So this kind of, if rearrangement is possible, then we will say that separation of variable method will work here. That means here in this differential equation, if I will be able to write all y variable, okay, in one side and all x variable in right hand side, so that means we can use separation of variables method. And if I'm saying y, that means that includes dy also. If I say x, that includes dx also. So here I can write dy by y, and here this is nothing but 5x dx, right? So here we can see that all y variables including dy is actually separated out from x variable with along with dx also, right? And we don't worry about the constant, right? Constant you can keep in any of these sides. And suppose you are not seeing any constant here, by default one is present, correct? No, so we don't worry about constant, fine. So that means if this kind of rearrangement is possible, then we can move forward to use separation of variables method. So this method is useful to solve D. So again I am saying that separation of variables method will not always work. Okay, fine. So here what we are seeing that this differential equation is okay, but what about our partial differential equation? And because we have to work on partial differential equation in today's class, so in which type of partial differential equations we will seek help of separation of variable method? So those type of partial differential equations which are linear homogeneous in nature, and again they will be having two variables, right? And with their linear homogeneous boundary conditions. Okay, we will discuss all those things. So those type of partial differential equations we can solve easily using separation of variables method, and we are going to see that the one dimensional wave equation actually satisfies all criteria to get solved by separation of variables method. Okay, and this method is actually simple, so we really want to use this method. Now we are going to see the solution of one dimensional wave equation. Now we are going to find the solution of one dimensional wave equation. Okay, so we had seen in last class only the equation of one dimensional wave equation, and what was that? It was my del 2u by del t square, okay, equals c square del 2u by del x square. Fine. So this equation actually is my linear homogeneous partial differential equation, right? And why I'm calling it linear homogeneous? So those things we have actually discussed in detail. If you have any doubt that what is linear or homogeneous equation, you can always refer those videos, because if we will discuss those things again, so it will be very long, right? Okay, fine. So this is our one dimensional wave equation. Remember, like we had seen that what is this u, we had seen one a diagram where we have said that this x-axis actually has the length, okay, of the string, and this y direction has u, right? And what is this u? U is the deflection in the string in y direction. Fine. We had taken example of a guitar string, right? That if suppose this is the string of guitar which is fixed both sides, and if we are actually plucking the string, so what happens? It starts vibration here, so it starts showing vibration, correct? So this equation only we had derived in last class, and today we are going to see the solution of this wave equation. Okay, so for that we had since got this equation, now we are going to find the solution of it. Okay, so this is u is deflection. What we had said that deflection is always in my y direction. We don't have deflection, or we are ignoring the deflection of our horizontal axis, because that deflection in horizontal axis is very negligible. So this u is only the deflection, right? So this u depends on two variables, correct? Which two variables actually are there? So at any point of time, this deflection actually is defined by the position, correct? Position of the string. So that means this u is actually, u depends on x, okay? And even it can be defined with my t also. So there are two variables, along with that u can be defined. Also we can see that u is dependent on t also, u is dependent on x also, and x and t are two independent variables. So these are the basic rules of our partial differential equation, which also we have covered. Fine. And we said that we are going to find the solution by separation of variable method, and separation of variable method actually gets applied on those type of partial differential equations which are linear in nature and which are homogeneous also, correct? Along with that, we have one more criteria. The criteria says that the boundary condition should also be linear homogeneous, right? What is my boundary condition here? So for that, if we will again think the setup of our string of guitar, so what we had said that we have actually fixed this guitar string on both corners, correct? And this string is stretched. That means the string has tension in it. So there are two concepts which we are going to discuss. One is called as initial condition. Okay, so one is called as initial condition, second one is called as boundary condition. So first we will talk about what is initial condition. So initial condition for my this setup of experiment is what? Here we will just say that the string is at rest. The string right now at time t equals 0, because when we have not started the experiment, when the time is 0 only, when t is 0, so the string is at rest. That means there is no vibration on it, there is no deflection on it. So we will be saying that the initial condition is what? That means the rate of change of deflection at time t equals 0 is 0, correct? No, at time t equals 0, what is happening? There is no rate of change of deflection. The string is just horizontal, just parallel to my horizontal axis. The string length, we are assuming this is L. So here we'll say that x-axis is 0, and here we'll say that at x-axis this is the coordinate L. When we pluck the string, so in that case what is happening? Here we have applied the force, correct? No, we are just pulling the string. The string has great tension in it, so we have pulled the string. So now Again, what will be the boundary condition? Boundary condition will be called as what? What is, I mean, happening in these two corners, in these two boundaries? So we will be saying that the boundary condition is what? That this u, which is, we'll say that the function of x and t. So when x is, the length is 0, correct? No, when length is 0 at any point of time, even the function, when length is completely L at any point of time, always this deflection will be 0. That means at these 2 points, only I'm talking about these two boundary points, there we won't be having any deflection, right? Even if we are stretching the string is having vibration. The boundary condition says that at these two corners there won't be any deflection. Deflection will be seen in all other places but not on the boundary condition, boundary places. So these two things are called as boundary condition as well as initial condition. And whenever we have plugged the string, this is only giving me the force. It all depends, like force is what? It is going to generate like how this deflection will happen. So if I am going to pull the string very high, or if I'm going to pull the string on some other place, suppose here, or maybe two places, or maybe three places, three points I'm going to pull, these all things will actually matter, that how the deflection will happen, how the vibration will happen, or how the wave will get generated. Okay, that generation of wave only we are going to discuss in our solution. Okay, because this u, we know that u depends on x and t, so we are going to find the value, the answer with respect to x also and with respect to t also. Okay, what we had said, that separation of variable method reduces the partial differential equation into two ordinary differential equations, because we have two independent variables. So it is going to reduce the equation into one equation which will be totally dependent on x, okay, and other equation which will be totally dependent on t. So it will be very easy to get the solution of the ordinary differential equation with respect to x and ordinary differential equation with respect to t only. Okay, and why I'm calling it ordinary differential equation now? Because the resultant equation, so if only one variable is present, so it will be called as ordinary differential equation, correct? No, this is my partial differential equation. Why? Because u depends on two variable. Okay, so somehow if we will be able to break this equation into two forms, where one form will be totally dependent on x and one form will be totally dependent on t, so in that case analysis of the equation will be much more easier. Okay, this is our one-dimensional wave equation. U is dependent on two independent variables. One is x and the other is t. Correct? This x is the function which is totally dependent on x, and t is the function which is totally dependent on t. Fine. So this first equation only we can rewrite as del 2. Instead of u, I am writing x and t both. Correct? No, this is called as product divided by del t square. And then right hand side will be what? C square is constant, we know, right? C square is the positive constant, right? So now this is my, again, del 2. Instead of u, I am writing down again x into t del x square. Okay, now so we are going to separate one type of variable in one side and the other type of variable in my other side. Okay, so for that, what I'm going to do, I'm going to rewrite it as, see, this is your partial derivative with respect to t. For that, x I am going to treat as constant, correct? No, if partial differentiation is with respect to one variable, so for that case, we treat the other variable constant. So I am writing down x del 2t by del t square, fine. Now this is c square is as it is. Now again, since here partial derivative with respect to x, so I'm treating t as constant, so writing down t outside. Now this is my del 2 capital X by del x square. This capital X is what? Function of x with respect to x only. Okay, so what I'm writing down, I'm dividing left hand side and right hand side both with c square xt all. Okay, so if I've divided it, so x and x will get cancelled. So I'm getting here del 2t by del t square, and then this is 1 by c square t. So this case is okay, right? No, So here I have one type of variable only along with one constant c square. Fine. Now what I am doing here? Here again I am writing down here again I am cancelling out c square and even t also. So I am getting 1 by x del 2x by del x square. Okay. So in this case what is happening? I can see that one type of variable is present in one side and the other type of variable is present in the other side. So if both are same, so I can say that I'm just equating them with some constant name. Suppose I'm giving some name k. Okay, that means this left hand side equals right hand side is nothing but some constant k. So in that case, what will happen? So if I will focus on this only del 2 t by del t square and 1 by c square t is already present, correct? No, if I'm saying that this equals k, what does it mean? Then I'm writing down, so I can rewrite it as 1 by c square t del 2t by del t square minus k equals 0, because I'm just taking this k also in my left hand side to make it right hand side 0. And then again what I can do, so further I want to simplify in this fashion so that denominator will not contain the c square t. What I can do for that, I can say that both left hand side and right hand side I am multiplying with c square t. Suppose I am multiplying my left hand side also, okay, and right hand side also with c square t. So what will happen here? So this is again 0 into this complete thing will become 0. So I'm doing it just to remove any quantity from my denominator. So it is nothing but del 2t by del t square minus c square kt equals 0. Fine, right? Now you can check that this is nothing but my ordinary differential equation with respect to del t. And if I am writing down one type of variable, okay, instead of del I can write down here d also. That means this I can write down d2t by dt square equals k. This is perfectly okay to write d instead of del, because if any one variable is present in my equation, so this will be called as ordinary differential equation. Then I don't have to write it partially. Okay, so this is nothing but d2t by dt square equals k. Okay, so and if I'm writing down here also d2t by dt square, then you can easily relate it with our differential equation which we have covered, right? This is nothing but one differential equation which I'm writing down. If d2t by dt square, if I'm writing down as d square, so it will be how much? D square t minus c square kt equals 0, right? Here what I am writing down, I am just saying that d by dt is my d, or d2 by dt square is nothing but d square. For that I have written down d square t minus c square kt equals 0. That means I have used the differential operator here. Okay. Okay, fine. So, but why I have done these things? Because this is now one ordinary differential equation, and to solve this differential equation is far easier than solving my partial differential equation. Similarly, I will be finding out differential equation that will be again another ordinary differential equation with respect to x variable only, right? So for that, what I will be writing down? So now I'm writing down here. That means again I'm writing down 1 by x del 2x by del x square, right? So if it is only one variable, so I can easily write down, instead of del I can write down d2x by dx square. Fine. So now because this has become my ordinary differential equation, this same equation I can rewrite as the same way as 1 by x d2x by dx square minus k equals 0, because I just want to take this k into my left hand side to make the right hand side 0. Fine. And similarly, like how we had done the previous one, we are multiplying the left hand side also and right hand side also with x, just to avoid my x in denominator. Okay, so I'm multiplying x in my left hand side also. Okay, and then this is my x into k, and again I am multiplying x with 0, so it will be 0 only. So in that case I can rewrite this equation as what? X gets cancelled. This is nothing but d2x by dx square minus kx equals 0. Fine. And again, if you will analyze this equation, this is nothing but my ordinary differential equation, which we used to solve using CF plus PI method, correct? No, here I don't have to find PI because my right hand side is not having any function. This is homogeneous. So I just have to find the complementary function. I will get the solution of this ordinary equation. Because of that only we have rearranged this equation in this fashion, right? So I will be writing down here d2 by dx square. Suppose I'm writing with a d operator. So it will be written as d square x minus kx equals 0, right? This is my second differential equation. And if I take x common, so this is nothing but d square minus k x equals 0. Fine. Yeah, right. So the same thing we have done. Fine. So here also we have done the same thing. We have got this equation just now and we had got this equation. Right. So now what we are going to do, these two equations only I have to analyze, and then I have to find the solution. But before solving these two equations, what we have to consider is this constant k, because we have only added this k, right? No, so this k, we said that this is just a constant. This constant can have values positive also, 0 also, negative also, correct? No, so to get the general answer of these equations, these two equations, we need to actually focus on the value of k also. So we will be having three cases, okay, for the solution of these two equations, these two ordinary equations we are going to solve by taking three cases. One case is what? When we will be thinking that k is 0. Second case will be what? When we will be saying that k is having some positive value. And the third case will be what? That k is having negative value, right? So we will be considering three cases to solve these two equations, and then finally it will be our answer. Okay, so this is my case 1, when we are saying that k is 0. Okay, so in that case our equation will become d square x equals 0 and d square t equals 0, right? Because now the k is 0, so this is d square k equals 0. K is 0, so c square k is also 0. That means d square t equals 0. So we have written down these two equations. Okay, so this is one simple ordinary equation. To solve ordinary equation d square x equals 0, what I have to write down? Since this is the homogeneous equation, we can say that my auxiliary equation of this equation is nothing but m square equals 0. Correct? No. What is auxiliary equation? In that case, we replace d operator with m and we don't write any variable here. So that means if my m square is 0, that means m is 0 and 0. That means that there will be two roots, fine, no? Because this is square. That means two values of m I am getting. Suppose if it was my m cube, so that means three values of m I had got. Okay. So I am getting m as 0 and 0. So what is the solution of differential equation? Solution of differential equation is what? The CF plus PI. But here we don't have to find PI because my right hand side is not having any function. This is just 0. So I just have to know what is CF of this equation, and then we are done with the solution. And we remember that what we had seen in CF lecture, right? So if the roots are same, okay, if the roots are same and real, so this was the form of my my CF, okay. So in this series, how many terms we are going to consider? Since only two values are there, right? Though the values are same, so we are going to take only two terms from this series, correct? No, so this is nothing but c1 plus c2x, okay, and then into e raised to mx. M is 0, so m is 0, so e raised to 0x, this will be nothing but 1. So here the answer is c1 plus c2x. Fine. So here we have got that this x is, right, so this u is nothing but x into t, where x we have got as c1 plus c2x. Similarly, for our d square t equals 0, the same thing. Here also we are going to get m is 0, 0 only, the same fashion. And then we are going to get two other names we have just taken for this constant. C1, C2 we have already used. So we are just using other names C3, C4. So this is C3 plus C4t. Fine. So u in this case, when k is 0, u is the product of x and t, and they are nothing but c1 plus c2x into c3 plus c4t. Fine. Now we are going to see the second case. Second case is what? Second case is my k is positive. Okay, so to say that k is positive, we are writing down k is, suppose some other name, that is p square. Why I'm writing down p square? Because if any value you are putting in p, suppose negative 5, negative 10, anything, and square of any positive or negative will give you positive only, correct? No. So to say that any variable is positive, we just write down as plus p square. Okay. So now the same way we are going to rewrite the equation. How we are going to write this equation? We had seen that here the equation which we had said, now my k is not 0, correct? K we have said that this is p square. Similarly, in this second equation also, k is not 0, k is p square. So my equation will become d square minus p square x equals 0 and d square minus c square p square t equals 0. Fine. So here that is only we have written down. Fine. So now what we are going to do? So this ordinary differential equation, since I have to solve, so I'm going to write the auxiliary equation, right? So for the first equation, the auxiliary equation will be what? So for the first equation, what is the auxiliary equation? We are replacing d with m and there won't be any variable present here. So this is your m square minus p square equals 0. Similarly, the second equation will have m square minus c square p square equals 0. There won't be t here. Fine. So in that case, what is my m? M is plus minus p. That is correct. Similarly, in my second equation, the auxiliary equation says that m is nothing but under root, so m is nothing but, right? So m is nothing but plus minus cp. Fine. Now we are, now what will be my cf of my first equation? So the roots are 2, because the equation is quadratic, so we will be getting 2 roots only, and these 2 roots are real and distinct. If the roots are real and distinct, so the CF says that it will be what? C1 e raised to m1. What is m1? M1 is the very first value of m, that if I am taking plus p minus p, anything I can take. So plus p and then x. Similarly, it is nothing but 2, because there are 2 roots only, so just taking 2 values. So this is C2 e raised to minus px. Fine. So we have got here also C1 e raised to px plus C2 e raised to minus px. Similarly, for my second equation also, we have got t equals how much? Some other name we have just taken, C3, C4, and here it is nothing but CPT and then minus CPT. Fine. Okay, so finally we got in the case 2, when k is positive, my u is x into t. And what is x? X is the same thing we have written and t is same thing we have written. But why I'm writing down here C1 dash and C2 dash, C3 dash and C4 dash? Because C1, C2, C3, C4 or this dash, if these all things are nothing but some constant, some different constant we don't know, right? So since we have already used the names C1, C2, C3, C4 in case 1, so just to say that it is not necessary that those constants and the case 2 constants will be same. We have just given some other name, C1 dash, even we can write down C4, C5, C6, C7, anything, right? Okay, now we are going to see the case 3. So case 3 is what? Case 3 is we have taken k as negative. So how to say that any quantity is negative? So we have just now said that to say any quantity positive, we say this is p square. That means p is positive or negative, anything, square of that is always positive, and negative of that always positive thing will be negative only. Fine, no? So to say any quantity that it is negative, we write down minus p square. So we have written down k is minus p square. So we are going to replace the equation is present here. We are going to replace this k with minus p square, and again in the second equation k with minus p square. So minus minus will become plus, so it will be my d square plus p square x equals 0. The second equation will become d square plus c square p square t equals 0. Fine, no? So here we have written down the same thing. And the same method we are going to find the auxiliary equation of first equation and auxiliary equation of the second differential equation. So auxiliary equation will be what? Here m square is minus p square, correct? So for that m will be imaginary. So for that m will be imaginary pair. It will be plus minus ip, and in my second equation m will be again imaginary pair of, this is plus minus icp. So again we had seen this formula also, correct? No. So if the roots are imaginary, so we get this as my cf. So in this case we'll see that there is no p present, correct? No, because there is no real part present here, this is 0. So for that, in this general form we will be using p as 0. So anything which has power 0, it will be 1 only. So the answer will be how much? It is your c1 cos qx, and what is your q? What is with your I? So the q is here my p. So I'm going to write here cos px plus c2 sine, again q will be, in this case q is nothing but p. So I'm writing down c2 sine px, correct? So fine. So this is the, yeah, we have got here. So this is nothing but the solution of x. Similarly, to get the solution of t, what we are going to write? We are going to use here q is cp. So we have used this q is cp, and then we got t equals c3 cos cpt plus c4 sin cpt, and then we have written down the u is nothing but x into t, which is the same reason we have used double dash here, and all these things and all other things are actually same. Okay, but now we have actually got three solutions, correct? No, in case 1, case 2, case 3, we have got three solutions of what? Of one dimensional wave equation. But which solution we have to consider and which solution we have to ignore, that we have to actually check. So we will move to the first solution. This is the first solution, right? So this solution says us that the final answer, this final answer is what? This is nothing but it should actually show the physical nature of one dimensional wave. Okay, and what is my one dimensional wave? We had discussed the complete property in last class, that this one dimensional wave equation should be having deflection, right, in this fashion. So this deflection is should be present in my y direction only, right? So fine. So this way of physical nature of wave should get satisfied in these answers. But here we cannot see any reason which is actually stating this physical nature. This is nothing but some algebraic function c1 plus c2x and into c3 plus c4t. So this equation, this solution is not actually showing us this physical nature of wave equation. So we will discard it. So we are going to see the second solution. Okay, so what the second solution says us? So this solution actually says that here this actually has exponential function and even minus exponential function also. That means sometimes what will happen, exponentially it is going up, and similarly it can come to exponentially less also. And if both exponential functions will be same, so they will be in the balanced scenario also. And that is also not describing the nature of wave. What is the nature of wave? What we have said that it is like this, right? So that means this has some sinusoidal function. Though this has very less slope, this is not in this fashion. We are not going to say that the wave will be in this fashion, but still it has deflection in y direction. That means it has the nature of sinusoidal function, but this solution does not explain this type of nature, correct? No, here this is exponential in nature. Okay, so the third solution actually says that it has cos function also, it has sine also, fine, and sine and cos both actually represent the wave in this fashion. Okay, this function actually perfectly describing the physical nature of the wave. Okay, so we will say that this is the answer of one dimensional wave equation. So basically we have seen all possible solutions of one dimensional wave equation, but the solution which actually satisfies the criteria of wave function, or which actually satisfies the physical nature of wave, is actually the solution number 3, when we have taken k as negative value. Okay, so this is how we get the solution of a one dimensional wave equation. Fine. So if you find this class useful, please like and subscribe my channel. Thank you.